The rapid development of military hardware and technology during World War II led to the creation of entirely new types of weapons. Among the innovations that had the greatest impact on aviation, the atomic bomb, radar, and jet and rocket propulsion really stand out. After the war, Soviet leadership made a massive push to develop these technologies. The aviation industry was expected to play a leading role. At the time, heavy bombers were the only way to deliver an atomic bomb. That is why development of the Tu-4 bomber started as early as 1945. This was the Soviet reverse-engineered copy of the famous American B-29. It was the aircraft that made history with the bombings of Hiroshima and Nagasaki. Later, in 1947, the Soviet Aviation Development Plan added a new, ambitious goal, creating all-weather jet interceptors. Prominent aircraft designers Pavel Sukhoi, Semyon Lavochkin, and Artem Mikoyan took on this challenging task. At the same time, specialized institutes began developing airborne radar systems for interception and targeting. The Soviet Union already had some experience building metric wavelength airborne radars like the Ganesh system. However, to significantly improve range and targeting accuracy, engineers decided to switch to the more modern centimetric wavelength band. The first Soviet radar system of this kind was named Tori. Alexander Slapushkin served as its chief designer. The system featured a scanning parabolic dish. It was designed to detect B-29 class aircraft at a range of about 6.5 nautical miles. Pavel Sukhoi initially took the lead in this intense race among the chief designers. By late 1948, he had developed the single-seat Su-15 interceptor. This fighter was equipped with two powerful RD-45 engines and armed with a pair of N-37 cannons. Factory testing began in early January 1949 and was progressing smoothly. But tragedy struck in the summer of that year. During one of its final test flights, the prototype crashed due to severe aerodynamic vibrations. Semyon Lavochkin and Artem Mikoyan joined the interceptor program a bit later. They were tied up developing the new MiG-15 and La-15 frontline fighters. The new project from Lavochkin was designated the La-200. Meanwhile, the design from Mikoyan was named the I-320. At the time, the Mikoyan Design Bureau was known for pushing new aircraft into testing in record time. True to form, the two-seat I-320 interceptor made its maiden flight as early as April 1949. It was powered by twin RD-45F engines and armed with 3 N-37 cannons. At first glance, it might have seemed like the team of Semyon Lavochkin was falling seriously behind. His engineers had spent considerable time carefully analyzing different power plant options for their interceptor. Initially, they considered using two British Rolls-Royce Derwent 5 engines, but they quickly abandoned the idea because they lacked sufficient thrust. They then had to choose between a pair of RD-45F engines or a single TR-3 turbojet. Based on military requirements, the aircraft needed to accommodate a two-man crew. This consisted of a pilot and a radar operator seated side by side in a spacious cockpit. Because of this, the designers went with a tandem layout. They mounted two RD-45F engines, one behind the other, inside the fuselage. Even though this layout closely resembled the Su-15 and I-320 aircraft, it had one very important difference. The La-200 featured smooth fuselage lines with a circular cross-section. It did not have the drag-inducing front engine bulge that plagued its competitors. The exhaust nozzle was angled away from the aircraft centerline. It was neatly housed under a dedicated fairing. To maximize speed, the wings were swept back at 40 degrees. At the same time, the designers took a risk. They increased the wing loading to about 49 pounds per square foot. This was done even though the military requirement was capped at 41 pounds per square foot. Additionally, to boost performance, they swapped the original RD-45F engines for the much more powerful VK ones. After the mock-up was officially approved in late February 1949, the factory kicked production into high gear. What set this interceptor apart from standard single-seat frontline fighters was its advanced avionics suite. The Tori A radar was paired with the Magni and Barry identification friend or foe systems. This allowed the pilot to detect, identify, and engage airborne targets. To ensure all-weather capability, the interceptor was equipped with an automatic direction finder. It also had a low-altitude radar altimeter and the advanced Maverick blind landing system. This avionics suite was not just for solo missions. When paired with the radar, it made group combat sorties more effective. One of the most interesting engineering features of the aircraft was its innovative thermal anti-icing system. It used hot bleed air directly from the engines. This heated the wing leading edges, the tail section, and the engine intakes. The dual-wheel main landing gear retracted completely into the fuselage. This was a trademark of the Lavochkin Design Bureau. It kept the wings aerodynamically clean and free of structurally weakening cutouts. Because the aircraft was significantly larger, engineers had to beef up the pneumatic and hydraulic systems. They also had to add hydraulic boosters for the flight controls. Furthermore, the sheer amount of new avionics required a complete redesign of the electrical system. This resulted in a powerful high-voltage alternating current network. When the engineers finished assembling Aircraft 200 and ironed out the initial defects, they were in no rush to roll it out to the flight line. Learning from the experiences of previous years, the Bureau developed an extensive ground testing program. This was a first in their history. All critical systems were tested under conditions that closely simulated actual flight. This cautious approach paid off entirely. During ground testing, they uncovered numerous serious issues with both the design and the build quality. If these issues had cropped up on the airfield, fixing them would have caused massive delays. Finally, on September 9, 1949, Aircraft 200 began its initial flight tests. By that point, its main rival had already been in flight testing for nearly 5 months. This was the Mikoyan-designed AN-320, also known as the R-1. However, that fighter turned out to be far from ready. Attempts to iron out its endless defects went nowhere. By November, testing of the first prototype had to be halted entirely. It was ultimately handed over to a research institute. There, it served as a testbed for the new Tori-A radar. The team of Artem Mikoyan threw all their efforts into the second prototype. This was the I-320, designated as the R-2. This one turned out to be much better. Instead of the older RD-45F engines, they installed the more powerful VK ones. They completely redesigned the cockpit for better visibility and added a reliable anti-icing system. This updated interceptor took to the skies in late December. Interestingly, Mikoyan also had a backup plan. His designers took a standard single-seat MiG-15 fighter. They turned it into an interceptor under the code name SP. They fitted it with a radar and armed it with a massive N-37 cannon. Even though this aircraft did not fully meet the strict military requirements, flying it provided invaluable experience. It was useful for developing similar radar-equipped fighters. By late fall, they had a working radar installed in the MiG-15. They started getting it ready for state trials. Returning to the Model 200, flight testing kicked off on September 16th. Veteran test pilots Stepan Mashkovsky and Andrei Kosarev were at the controls. At first, the aircraft weighed about 22,000 pounds. This was because it was carrying a mock-up instead of a heavy, fully functional radar. During these initial flights, the Model 200 showed solid speed and climb rates. It accelerated to roughly 680 miles per hour. This was at an altitude of about 11,500 feet. It could climb to over 16,000 feet in under 2.5 minutes. It could punch through 33,000 feet in less than 6 minutes. Its service ceiling reached nearly 50,000 feet. But it was not all smooth sailing. The aircraft suffered from significant stability and handling issues. The pilots had to practically stand on the rudder pedals and muscle the control stick. In flight, the plane had a constant tendency to roll to the right. Because of these issues, the prototype was sent back to the factory. It needed urgent modifications on December 1st. Engineers had to counteract the heavy stick forces. They added controllable trim tabs to the ailerons. This allowed the pilots to balance the aircraft across different flight regimes. To completely solve the rolling tendency, they took a much more radical approach. Designers actually altered the right wing angle of incidence. They changed it by 15 arc minutes. They also tweaked the flight controls. Finally, they installed the actual radar equipment. With all these upgrades, the aircraft weight bumped up to around 22,500 pounds. Because of this, the team expected a slight hit to its speed and maneuverability. The modified Model 200 returned to the airfield on January 13, 1950. Right off the bat, the test flights proved the troubleshooting was a success. Most of the quirks were ironed out. The annoying right-wing roll was completely gone. In early February, the team successfully flight tested the Tory A radar system and its related avionics. Testing was split into two phases. First, they checked the system on its own. Then, they ran interception profiles against an Li-2 target aircraft. The test pilots made 6 passes at the target from just over 4 nautical miles away. The engineers monitoring the flights were pleasantly surprised by the radar image quality. Both the target and the ground clutter below were clearly visible. Overall, the factory test program was intense. The pilots completed 40 sorties. They logged just over 18.5 hours of flight time. This phase officially wrapped up on February 10th. The promising aircraft 200 was handed over for the much more rigorous phase of state trials. Slightly earlier, a single-seat Mikoyan fighter, known as the SP, had been sent for the exact same state trials. Around the same time, testing of the Tory A radar got underway on the I-320 aircraft. This process was overseen by a special government commission headed by Lieutenant General Yevgeny Savitsky. However, the initial results were far from encouraging. The Tory A radar system was still very immature. It was plagued by constant malfunctions. Target detection range fluctuated wildly. This happened even when tracking a massive Tu-4 bomber right from its 6 o'clock. The range jumped between roughly 1.5 to 4 nautical miles. The hardware simply kept breaking down. As for the single-seat SP fighter, the commission delivered a harsh verdict. Deploying it in actual combat was simply impossible. Not only was the radar unreliable, but the pilot workload was unsustainably high. The pilot had to fly blind on instruments while also operating the radar during an intercept, keeping their eyes glued to the scope. That was too much task saturation for a single pilot to handle. The 200 prototype entered testing shortly after. It was put through an extensive endurance test involving numerous sorties. The commission viewed the Tory radar with heavy skepticism and the program nearly stalled. The deadlock was only broken after an appeal from the chief designer, Semyon Lavochkin, to the government leadership overseeing the aviation sector. On April 12, 1950, Aircraft 200 became the first 2-seat interceptor officially cleared for state trials. It was a major milestone for the design bureau. State trials kicked off at a rapid pace. In just a few weeks, from mid-April to early May, test pilots logged over 36 test flights. This demanding work was entrusted to experienced military pilots Ivan Juba, Vasily Ivanov, and Vladimir Trofimov. The pilots deliberately pushed the aircraft to the edges of its flight envelope to evaluate its handling. That was exactly when new issues began to surface. For instance, if the pilot pulled the rear engine back to idle at speeds above 400 miles per hour while pushing the front engine to full throttle, the aircraft tail section would experience severe buffeting. Another unpleasant surprise emerged at speeds above 500 miles per hour. The aircraft would develop an uncommanded left roll. On top of that, the dual-wheel landing gear turned out to be fragile and failed frequently. Meanwhile, the onboard RSIU-3 radio suffered from constant glitches. With this mounting list of discrepancies, trials had to be halted on May 3rd. Aircraft 200 was sent back to the factory for major rework. To figure out why the aircraft was experiencing such severe buffeting, engineers had to conduct another 24 dedicated test flights. Investigating this technical mystery revealed a fascinating aerodynamic quirk. It turned out that when the pilot throttled back the rear engine, the airflow around the fuselage changed dramatically. This created a severe low-pressure zone toward the front. It built up a thick boundary layer of stagnant air. As this unstable flow reached the tail, it rolled into powerful vortices. These vortices battered the airframe, causing the shaking. To make matters worse, the reduced thrust from the rear engine meant its exhaust wash was too weak to break up and stabilize this turbulent airflow. Military technicians brainstormed a workaround. They suggested flying with the access doors near the rear engine bay left open. This trick helped bleed off the trapped air and the buffeting disappeared. To fix the problem for good, designers installed automated vent doors in the tail section. These were designed to pop open on their own whenever the pilot reduced RPM on the rear engine. On top of that, engineers reshaped the fairing, blending the vertical stabilizer into the fuselage. They also improved the sealing around the exhaust ducting of the rear engine. To figure out why the aircraft was experiencing an uncommanded roll in flight, engineers mounted 2 film cameras to monitor the left and right wings. It turned out the main culprit was the right wing flap. The uplocks were too weak. This allowed the aerodynamic loads to push the flap down slightly during flight. To fix this issue and improve the overall handling of the aircraft, the flaps were stiffened. The locking mechanisms were also beefed up. Additionally, narrow metal tabs about 1.5 inches wide were attached to the trailing edges of the wings. These acted as ground-adjustable trim tabs. They could be manually bent to compensate for any slight manufacturing asymmetry in the airframe. Designers also reinforced the wings using steel and duralumin inserts. This boosted their overall structural strength by almost 1/3. And for more responsive control, they stopped relying on a single central hydraulic actuator in the cockpit. Instead, they installed 2 separate actuators directly out in the wings. Beyond that, the landing gear, struts, and doors had to be redesigned. This was because the old dual-wheel setup was replaced with new, larger single wheels featuring upgraded brakes. Engineers also turned their attention to the radio gear. It was mounted too close to the exhaust duct of the forward engine and kept overheating. So they plumbed in a dedicated RAM air cooling line specifically for it. Once all these major kinks were ironed out, the second stage of state trials began. From late July to mid-September 1950, test pilots logged another 57 flights in aircraft 200. The 200 prototype demonstrated strong flight characteristics. It hit 655 miles per hour at an altitude of about 14,700 feet. This exceeded the initial speed requirements of the military. However, its clean range at 33,000 feet was only 550 nautical miles instead of the expected 810. With drop tanks, though, the aircraft met the requirement. It was capable of covering 1,080 nautical miles. On the controls, this heavy interceptor handled like a much lighter fighter. But it was not without some dangerous design flaws. For instance, the hydraulic flight actuators would starve under negative Gs. During an August test flight, the aircraft flew inverted for 15 seconds. After that, the controls completely locked up. When the pilots tried to roll back upright, the fighter unexpectedly snapped into a steep, descending left spiral. The crew had to muscle the controls together, chop the throttles to idle, and deploy the speed brakes just to recover the aircraft. During the pullout, airspeed peaked at 630 miles per hour, pushing Mach 0.98. The airframe also pulled 5 Gs. Furthermore, at speeds above Mach 0.82, the aircraft would experience buffeting when carrying drop tanks. To make matters worse, during high G maneuvers, the guns frequently jammed. They proved unreliable. Despite these issues, the evaluation board graded the trials as satisfactory. The primary stumbling block turned out to be the new radar. The older Tory radar system had already failed during state trials on the competing I-320R1 interceptor, and on the 200 it constantly locked up and malfunctioned. Out of 19 test sorties, only 3 were completed successfully. Fortunately, engineers were already working on newer, more advanced radars. These included the single-antenna Corsian system and the dual-antenna Izumrud system. Form factor-wise, these new units were almost identical to the old radar. This meant engineers could retrofit either system into the 200 without requiring major structural changes. Ultimately, the military brass opted for the Corsian radar. Meanwhile, their rivals at the MiG Design Bureau were trying to push their new I-320R2 interceptor through state trials. However, the aircraft suffered from the exact same teething issues as their first prototype. By September 1950, the airframe had racked up a solid 100 factory test flights, but engineers still could not iron out its critical flaws. Time was running out. On September 20th, the I-320R2 was pushed into state trials in an unfinished state. Unsurprisingly, no miracles occurred. Just 10 days and 24 flights later, it was dropped from the testing program. The culprit was the dangerous instability of the aircraft as it approached the speed of sound, specifically between Mach 0.89 and 0.90. It also suffered from a severe, uncontrollable wing drop whenever indicated airspeed exceeded 520 to 575 miles per hour. Despite the progress made during testing, by late 1950, The future of the 200 looked just as uncertain as the fate of the ING-320. The issue was that the Ministry of Aviation Industry and the Air Force were still betting heavily on all-weather interceptors armed with conventional cannons. But now they were facing a completely different approach, building an integrated air defense network based around cutting-edge guided missiles, including both surface-to-air and air-to-air variants. As geopolitical tensions rose and the reality of the Cold War set in, Soviet leadership reassessed their air defense capabilities. The reality was stark. The Soviet Union had almost no way to defend its key military and industrial cities against large-scale nuclear bomber raids. The existing radar systems and cannon-armed interceptors were severely limited. To score a kill, the interceptor had to be guided perfectly by ground controllers and execute a stern attack, slotting in right behind the enemy bomber. According to experts, the probability of shooting down a single high-speed target was no better than 60%, even if the target was flying straight and level without taking evasive action. If the enemy bomber started maneuvering or employing electronic jamming, those chances dropped significantly. In the era of nuclear bombers, the old concept of relying solely on aircraft guns was becoming obsolete. The Ministry of Aviation Industry had previously underestimated the potential of guided missiles, and aircraft designers were out of time to develop weapon systems from scratch. As a result, a massive push was made to develop a dense ring of surface-to-air missiles to defend Moscow. To pull off this ambitious project, they brought in the design bureau of Semyon Lavochkin, tasking them with creating the first Soviet surface-to-air missile, the V-300, as well as the G-300 air-to-air missile. This sharp pivot toward missile technology meant that the top leadership started losing interest in traditional all-weather interceptors. However, officially, nobody had canceled the previous requirements, so the Lavochkin Bureau kept working. Their main goal was to equip Aircraft 200 with a new, more powerful radar called the Korshin. To make this happen, the engineers had to completely redesign the nose section of the fighter. They moved the radar antenna slightly higher and reshaped the air intakes. This yielded an unexpected aerodynamic benefit. It completely eliminated a dangerous tail buffeting issue. This problem used to occur whenever the pilot throttled back the rear engine. On top of that, the designers wanted to increase the roll rate and overall responsiveness of the aircraft. To do this, they added new control surfaces to the wings known as spoilers. Moving some of the heavy radio equipment into the nose of the aircraft freed up valuable space in the tail section. This allowed engineers to increase the internal fuel capacity by 66 gallons, though for the time being they had only tested this modification on a mock-up. To keep the external drop tanks from creating excessive drag, they were mounted on longer pylons. At the same time, the engineering team resolved all the previously identified issues with the cannon armament of the fighter. In January 1951, after a series of major technical upgrades, the modified La-200 entered its next phase of flight testing. First, it went through rigorous factory checks. By the spring of that same year, it successfully completed official state acceptance trials. To thoroughly prove the reliability of the aircraft, test pilots flew 129 sorties. It is worth noting that 40% of these were flown in severe IMC. These conditions included heavy overcast, rain, and snow. The ceilings dropped to a critical 500 feet, and cloud tops exceeded 31,000 feet. Another 12 flights took place at night. All in all, including the earlier factory tests, the interceptor logged a total of 243 flights. The results of these rigorous trials were a pleasant surprise for the engineers. The overall performance of the aircraft had noticeably improved. The top speed of the interceptor reached 665 miles per hour at an altitude of over 16,000 feet. It took exactly 6 minutes to climb to 33,000 feet. Its service ceiling was pushed to 51,000 feet. Thanks to the 66-gallon increase in internal fuel, the high-altitude clean range reached 632 nautical miles. This extended to 1,171 nautical miles with the use of drop tanks. However, there was one major setback. The onboard Korshin radar proved to be defective, so it was deemed untestable. Radar trials were postponed until the summer. Despite this, the State Commission delivered a favorable verdict. The La-200 successfully passed all its tests and was recommended for production. The board noted that the airframe could accommodate either the Korshun radar or an alternative system called the Izumrud. The final choice of avionics would be made at a later date. Meanwhile, the direct competitor to the La-200, the I-320, was also trying to pass its second round of state trials, but fate was far less favorable. The engineering team never managed to fully resolve the design flaws of the aircraft. What is worse, a serious accident occurred during weapons testing. A cannon round detonated prematurely just outside the muzzle. As a result, the nose section of the aircraft suffered catastrophic damage. Lengthy repairs and constant attempts to fix the design severely dragged out the testing process. By the end of April 1951, the I-320 project was officially rejected. This turn of events made the La-200 the clear winner. In 1951, it stood as the only Soviet all-weather interceptor that had not only successfully passed all state trials, but was also fully ready for mass production. At the end of May, a draft decree was sent to the Council of Ministers to put the aircraft into production at the Gorky Aircraft Plant. Upon entering service, it was slated to receive a new operational designation, the La-17. The Aviation Ministry had already started tooling up the production lines. They expected the military to take delivery of the first 50 fighters by the end of the year. But in an unexpected twist, this ambitious decree was ultimately never signed. This was driven by a massive shift in priorities. A special commission tried to iron out issues with the problematic Korshun radar, which had already caused the lightweight Yak-50 interceptor to fail its flight tests. Meanwhile, a completely new strategic concept was taking shape among the military brass. Soviet leadership realized they needed an all-weather patrol interceptor to protect the vast, remote territories of the far north and the Russian far east. Building surface-to-air missile sites out there was just too difficult and impractical. This meant the skies had to be defended by aircraft capable of flying long endurance patrols. The design bureau of Alexander Yakovlev was brought in for this project. The team was tasked with creating the brand-new Yak-120 interceptor. They planned to equip it with the promising Sokol radar. This system could track targets from up to 16 nautical miles away. The aircraft would also feature two new, highly fuel-efficient AM-5 engines. With these new power plants, the aircraft could fly roughly 1,600 to 1,900 nautical miles. This culminated in a major meeting in the office of Joseph Stalin in early August 1951. During this meeting, the future direction of Soviet aviation was finalized. The Mikoyan Design Bureau was ordered to create a new escort fighter based on the proven MiG-15. At the same time, the team from Yakovlev was tasked with developing a powerful, two-seat, long-range heavy fighter. This aircraft was slated to be produced as both a patrol interceptor and a reconnaissance aircraft. The face of the Cold War in the air was beginning to change rapidly. However, this long-term strategy left the air defense forces without an immediate solution. The new interceptors from Mikoyan and Yakovlev were at least 2 years away from active service. To bridge this gap, the military pushed to put the existing Model 200 prototype from Lavochkin into mass production as a stopgap interceptor. They insisted that the aircraft be urgently upgraded to meet new requirements, including an extended flight range and the integration of modern search and track radars like the Korshun or Izumrud. The Lavochkin Design Bureau, already heavily occupied with missile development, reluctantly took on the task of adapting the airframe. In mid-November 1951, the new assignment was officially approved with an incredibly tight deadline. The upgraded aircraft had to be ready for state acceptance trials by April 1952. An additional directive required the aircraft to carry unguided rocket loadouts, such as ARS-212, TRS-190, or ARS-57 rockets. The fully developed rocket launchers had to be demonstrated by September 1952. Meeting these kinds of ambitious requirements would have meant radically overhauling almost the entire design of Aircraft 200. But the prototype facility was already stretched to the limit with missile programs. Because of this, it became absolutely clear that the engineers would only have time for a partial upgrade of the existing prototype before the deadline. Because they were so strapped for time, the developers decided to split the work into 2 parallel tracks. The first option was an aircraft with minimal changes. It was intended purely for construction and baseline testing. It was designated as the 200B. The second option was an aircraft that would fully satisfy all the requirements of the military. If successful, it would go into full-scale serial production under the designation 200BF. To significantly boost the flight range for the 200BF model, the engineers designed a completely new wing. On the outside, its shape and aerodynamics looked almost exactly the same as the old one. However, its internal structure was radically different. Inside each wing half, they fitted integral fuel tanks. These tanks held roughly 260 gallons each. Beyond that, the structure was specifically reinforced in the areas where rockets and external drop tanks were going to be mounted. On the simplified 200B version, however, they kept the old wing. They just beefed it up a little so drop tanks could be carried underneath. Since there was no internal space for fuel in this version, the drop tanks had to be made much larger and bulkier than the ones on the fully fledged 200BF model. Installing the new radar required extensive modifications. They had to rework not just the nose, but the center fuselage as well. The massive antenna for the so-called radar was housed under a large radome that took up almost the entire nose section. To ensure the engines received adequate airflow, engineers added 3 protruding air scoops. But this design choice came with a steep penalty, significantly increasing aerodynamic drag. These modifications made the aircraft substantially heavier. The design bureau hoped to offset the resulting loss of speed and maneuverability on the 200BF model. To achieve this, they planned to install a more powerful, afterburning VK1F engine in the aft fuselage. For the baseline 200B variant, however, they decided to leave the power plants unchanged. The so-called radar itself turned out to be much heavier than anticipated during the design phase. To prevent the aircraft from becoming dangerously nose-heavy and shifting its center of gravity out of limits, the wing root had to be moved slightly forward. This was a fix they applied to the upcoming 200BF model. But for the already assembled 200B airframe with the original wing configuration, the issue was solved with a crude, brute force solution. They simply packed over 660 pounds of ballast into the tail section. This extra weight introduced a new problem. The aircraft now required reinforced landing gear. Oddly enough, the wheels turned out to be the primary stumbling block that kept the 200B from beginning its flight tests on schedule. The issue was that the tires on the baseline 200 model had already been upgraded twice. The designers flat out refused to reinforce the same wheels a third time. Swapping them out for larger ones was not an option due to the restrictive size of the wheel wells. This landing gear saga caused significant delays, but the engineering team eventually found a compromise. Finally, in June 1952, the 200B rolled out onto the tarmac. After thorough ground checks, full-scale flight testing kicked off on July 3rd. Experienced test pilots took the controls. Alexei Kokotkov was in the cockpit alongside colleagues like Yakov Vernikov, Vasily Komarov, Konstantin Makarov, and Alexander Kosarev. Those early flights confirmed the worst fears of the engineers. The performance of the aircraft had dropped noticeably compared to its predecessor. The top speed of the jet now barely reached 640 miles per hour. It took a full 7 minutes to climb to 33,000 feet. Its service ceiling sat at roughly 46,000 feet. Its range without external drop tanks was limited to a modest 518 nautical miles. By the end of the summer, test flights had to be put on hold. Up until September 8th, mechanics worked on the aircraft. They installed beefed-up landing gear and fitted new air scoops for the aft engine. These intakes had been refined based on recommendations from specialists at SAGI, the Central Aerohydrodynamic Institute. The upgrade paid off. During a test flight on September 9th, the aircraft managed to squeeze out an extra 6 miles per hour in top speed. However, flights were soon halted once again. This time, the aircraft was being prepped for combat trials. Crews installed rocket armaments, tested external drop tanks, and evaluated how the airframe handled the resulting vibrations. By that point, the 200B had completed 32 flights. It had logged a total of 18 hours and 28 minutes in the air. While the struggle with excess weight dragged on, over at another design bureau, Alexander Yakovlev had something of his own to show off. Running a bit behind schedule, the brand new Yak-120 finally rolled out for factory trials in July 1952. This fighter was a clean-sheet design built to meet the latest military requirements. Powered by new compact engines, the Yak-120 ended up being much lighter and smaller than its rival, the 200B. Throw in 45-degree swept wings and you had an aircraft that easily outperformed the 200B across the board. By November, factory testing of the Yak 120 was nearly complete. But there was one massive problem. The aircraft was flying without radar. Development of the so-called radar system was falling disastrously behind schedule. This left them with absolutely nothing to equip the fighter with for its state trials. The engineers went with the only logical solution. They installed the Izumrud radar instead. This was the very first Soviet radar system to successfully complete its trials in early 1952 on the single-seat SP-5 fighter of Artyom Mikoyan. After this, it was recommended for serial production. So, in early December, the Ministry of Aviation Industry made a tough call. They ordered the Yak 120 to be hastily equipped with the Izumrud system and sent straight to state trials. Meanwhile, the design from Semyon Lavochkin, the 200B, was converted into a flying testbed for the Scientific Research Institute. Its sole purpose now was to flight test that problematic so-called radar. And with that, its rivalry with the Yak 120 effectively came to an end. Eventually, a fully functional so-called radar was installed on the 200B. Integration testing began in the first half of 1953. Mark Gallet took on the role of chief test pilot for this phase. On June 26th, official state trials for the new radar kicked off at the Air Force Scientific Research Institute. Thanks to this engineering work, the technical bugs were ironed out, improving the reliability of the system. All in all, getting the so-called radar properly dialed in required the 200B to fly 109 test sorties. In the first half of 1953, the Yak 120 prototype equipped with the Izumrud radar successfully completed its state trials. By November, engineers had sorted out all the identified issues and run final checks. In this exact configuration, the fighter was officially accepted into service. Meanwhile, development of the more powerful so-called radar was also wrapping up. Its design had seen major improvements, so in November 1953, an order came down to stop testing the radar on older prototypes and install it straight into the new Yak 120. In April 1954, the final phase of state trials for the radar on the Yak 120 wrapped up. The brand new system was then cleared for serial production. By September 1954, the first production two-seat interceptors equipped with the Izumrud radar started rolling off the assembly line. This version of the aircraft was designated the Yak 25. Shortly after, starting in January 1955, the military began receiving the modified Yak 25M. This aircraft came factory equipped with the so-called system. That is how the complex saga of developing the first all-weather jet fighters of the Soviet Union came to a close. This journey of continuous development and testing had stretched out over 8 years. The design bureau led by Semyon Lavochkin accomplished a significant engineering task. Starting practically from scratch, their team managed to develop the first Soviet jet interceptor. However, this success was overshadowed by shifting priorities. The bureau was ordered to pivot and focus exclusively on missile technology. As for the fate of the La-200, it was a capable aircraft that demonstrated strong performance after its initial flaws were corrected. But ultimately, the design arrived right at a historical turning point when guided missiles began entering widespread service. This new technology was forever changing the rules of air combat.